So in this video, we will take a little bit of time to talk about horizontal asymptotes. So the directions for this problem ask us to locate the horizontal asymptotes of this function here. And then we're also going to be trying to determine if the asymptote is located on both edges of the graph. So are we approaching the same value as x extends way over to this edge? And as we go over to the right edge of the graph, x would be going to positive infinity. Do we get a different value or the same value as we approach negative infinity, because that would be the x value that we approach at the left edge of the graph. So I started with the right edge of the graph, so I just dove right in. I checked the limit as I'm approaching infinity. What ends up happening when you try to put infinity in place of the x's, you end up with infinity plus 6 in the numerator, which is infinity. Infinity squared is still infinity. Adding 3 times infinity onto that is still infinity. Subtracting 18 from a value that's never going to stop growing is still going to leave you with a value that's never going to stop growing. So we end up with infinity over infinity. So this right here, infinity over infinity, is one of the trickier things to deal with in calculus. If you've seen L'Hopital's rule, by the time you're watching this, you know a way that's pretty effective to handle this in pretty much all situations. What I'm about to go through here would be prior to having discussed L'Hopital's rule. If you're doing a limit as you approach infinity and you're dealing with a polynomial divided by a polynomial, which this function is that type, you can use a strategy similar to what I'm going to suggest as we talk through this next line. So here's what I think when I see this, and I'm not going to be using L'Hopital's rule to evaluate the limit. This signals that I've got to do some algebra to get something to cancel. And when you have a polynomial over a polynomial, if you just take the highest power of x from the numerator, and if you factor that power of x from the numerator, it's easy to factor x from x, you're going to be left with 1. It's a little different and kind of weird to factor x from 6, but if you're factoring x out of something, you're needing to divide what you begin with by what you're factoring out. And the reason why division is the operation here is because I have to be able to undo this set of parentheses. I have to be able to distribute this x back in and get back to what I had in my original numerator. And if I distribute x into 1, I definitely get back to x. If I distribute x into 6 over x, the x's are going to cancel and I'm just left with 6. So it's a little different. It's not that comfortable to do, but you'll see in a minute why this is definitely beneficial to us in this particular situation. Did the same thing in the denominator. My highest power of x was x squared, so I factored x squared from x squared. I factored x squared from 3x. So if I'm factoring x squared from this, I have to divide this term by x squared. And if I divide x by x squared, I'm going to have one of the x's in the denominator cancel with the only x from the numerator, and that'll leave me with 3 over x. If it helps to think about distributing x squared into this middle term, 3 times x squared is 3x squared. 3x squared divided by x does take me back to 3x after I do the cancellation. So once again, it's weird, it's uncomfortable, but it's going to benefit us, and you'll see why pretty soon. I am factoring x squared from the 18 as well, so I have to divide 18 by x squared, and that'll leave me with this. And once again, if you check the distribution in the denominator, distribute x squared into all 3 of these terms, you'll see that we do get back to that original denominator. So what I've also done, and you see in green here as I've been pointing at this line, I have done some cancellation. Once this is multiplication between the terms of the numerator, the pieces of the numerator, and I also have multiplication between 2 separate factors of the denominator, I can cancel anything that's a common factor shared between the top and bottom. So because I have an x times something else in the numerator, and x squared is x times x, so I can take one of those x's from the x squared, and I can cancel with the x that's multiplying the set of parentheses in the numerator. And then if you look at this next line, one other thing I did was I didn't necessarily like dealing with the denominator in the form that it's in right here after canceling the x's. So I distributed that x back in, right? So I distributed x into the 1, x into the 3 over x, so the x's cancel and I'm just left with 3. And then if I distribute x into this term, I'm going to have the x that I distribute in cancel with one of the x's from the denominator, leaving me with this. So here's why this gets us to a conclusion when we use this process when checking this type of limit as we approach infinity. I put infinity in place of this x, and this x. And what ends up happening is 6 divided by a million, 6 divided by a billion, 6 divided by a trillion. As that denominator grows and grows and grows within this individual fraction right here, that fractional value is going to tend to 0. Using the same exact argument, this fractional value is going to tend towards 0. So a number that's fixed divided by a number that's going to be growing forever is always going to be a fractional value that's going towards 0, regardless of how big or little your numerator is. So if these are tending to 0, I've got 0 there, 0 there. That's easy for the numerator. 1 plus 0 is just 1. Sorry about that. In the denominator, I have infinity in this spot, right? I still had to replace that x with infinity. So infinity plus 3 minus 0. Well, if I'm at infinity and I add 3, I'm only growing more quickly. So that's still going to be infinity. And just like we said a few seconds ago, a number divided by infinity is always going to tend to 0. So on the right edge of this graph, as x approaches infinity, what we've just determined is that our y value tends to 0, and that tells us that we do have a horizontal asymptote of y equals 0 on the right edge of the graph, because we've just considered what happens as we approach infinity. Now the left edge of the graph is going to involve x approaching negative infinity. The nice thing about this process, when you're applying it to a rational function, when you're applying it to a polynomial over a polynomial, you're going to still get an indeterminate form, plus or minus infinity over plus or minus infinity. You're still in need of doing some algebra. The algebra doesn't change. The algebra that gets to the point where something cancels is the exact same sequence we went through back here. So what I did when I checked my limit as I went toward negative infinity, I just went to this, I'm going to say simplified, maybe I should call it beneficial. I'm going to go to this beneficial form of the original function, put negative infinity in place of all the x's. And what ends up happening there is, although this is 6 divided by negative infinity, 6 divided by negative a billion is still a fractional value that's tending to 0, as is 18 divided by negative a billion. So these are still tending to 0. Technically, I have a little bit of an omission here. This should be negative infinity in the denominator. My answer doesn't change. 1 divided by negative a billion is still a fractional value that's really, really close to 0. So what this limit tells us is that as we go to the left edge of our graph, as x goes to negative infinity, y approaches 0, and that tells us that this asymptote is located on the other edge of the graph as well. So we have a horizontal asymptote of y equals 0 on both edges of the graph. Just to confirm this, I went ahead and produced a quick graph on Desmos. You could do it on your calculator as well. So as we go to infinity, what y value are we leveling off at? Definitely looks like 0. As we go to negative infinity, what y value are we leveling off at? Definitely looks like 0. So in conclusion, when you're checking a limit as you approach infinity or negative infinity, and it's a polynomial divided by a polynomial, using a strategy very similar to what I've suggested here is going to work pretty effectively. Now, if the function that you're doing this analysis for changes, if it's something that involves absolute values, or it's something that involves the natural base, e to a power, an exponential function, you're going to have to make some little tweaks. But anytime you're looking for asymptotes, you need to check 2 horizontal asymptotes. You need to check 2 limits, approach infinity, approach negative infinity. This process works well for a rational function, polynomial divided by polynomial.